Hello science explorers! Today we are diving deep into something truly amazing, waves. Now what exactly is a wave? Well, imagine you are at a beach, you see those big rolling things in the ocean, those are waves. But waves are much more than just water, they are a way that energy travels from one place to another. It's like a messenger carrying a package of energy. This energy can move through water, through the air, or even through empty space. It's a fundamental part of how our universe works, pretty neat, huh? Think about sound. When I talk, my voice creates sound waves. These waves travel through the air to your ears. That's how you hear me. Or think about light. Light from the sun travels to Earth in waves. This light allows us to see everything around us. Without light waves, our world would be very, very dark. Even things you might not immediately think of, like radio signals for your favorite music or microwaves that heat your food, are types of waves. They are invisible messengers, constantly moving and carrying energy. Alright team, let's get specific and talk about a super important part of a wave. Its wavelength. Imagine you are looking at a wave in the water, you see those peaks, the highest points of the wave, and you see those troughs, the lowest points? Well, the wavelength is simply the distance from one peak to the very next peak, or you could measure it from one trough to the very next trough. It is the length of one complete wave cycle. Think of it like measuring how long one wiggle of the wave is. If you drop a pebble into a calm pond, you will see ripples spread out. These ripples are waves. The distance between the crest of one ripple and the crest of the ripple right next to it is the wavelength. Knowing the wavelength is super useful because it tells us a lot about the wave's properties and how it will behave. For instance, the color of light depends on its wavelength. Next up on our wave exploration is frequency. This sounds a bit technical, but it's actually quite simple. Frequency tells us how many waves pass a certain point in a certain amount of time. Imagine you are standing by the seashore watching the waves roll in. If you count how many wave crests pass you in 1 minute, that's related to the frequency. Scientists usually measure frequency in hertz, which is abbreviated as She. 1 hertz means 1 wave cycle passing by per second. So if 5 waves pass a point in 1 second, the frequency is 5 Hz. Easy peasy. Think about wiggling a rope. If you wiggle it slowly, you create waves with a low frequency. Not many waves pass a point each second. But if you wiggle the rope really fast, you create waves with a high frequency. Lots and lots of waves will pass by every second. Frequency is all about how often the wave pattern repeats itself at a single point. High frequency means lots of wiggles in a short time. Low frequency means fewer wiggles in the same amount of time. Alright science adventurers, we've talked about wavelength, how long a wave is, and frequency, how often it wiggles. Now, let's talk about amplitude. Amplitude is all about the wave's intensity or strength. Imagine our ocean wave again. The amplitude would be how high the wave rises above the normal, calm sea level, or you could measure it as how deep the trough dips below that calm sea level. It's the maximum displacement or distance moved by a point on a vibrating body or wave measured from its equilibrium position. It's basically the wave's height. Think about turning up the volume on your stereo. When you make the music louder, you are increasing the amplitude of the sound waves. The sound waves are carrying more energy, so they make your eardrums vibrate more strongly. That's what you perceive as loudness. A quiet whisper has sound waves with a small amplitude. A loud shout has sound waves with a much larger amplitude. So amplitude is directly related to the amount of energy a wave carries. More amplitude means more energy. It's the muscle of the wave. Consider light waves. The amplitude of a light wave is related to its brightness. Section 5. Doing the wave dance, transverse waves explained. Now that we know about wavelength, frequency, and amplitude, let's talk about different types of waves. First up, we have transverse waves. The word transverse means situated or extending across something. In a transverse wave, the particles of the medium, that's the stuff the wave travels through, move in a direction that is perpendicular or at a right angle to the direction the wave itself is traveling. Imagine you and a friend are holding a long rope. If you flick your wrist up and down, you'll send a wave traveling along the rope towards your friend. Notice something cool? The wave travels horizontally along the rope, but each little piece of the rope itself just moves up and down. It moves vertically. The motion of the rope particles, up and down, is perpendicular to the motion of the wave, sideways along the rope. That's the key characteristic of a transverse wave. Section 6, the push and pull, exploring longitudinal waves. Alright, Science Squad, we've mastered transverse waves. Now let's meet their equally cool, sibling longitudinal waves. These waves are a bit different in how they make the medium move. In a longitudinal wave, the particles of the medium vibrate back and forth in the direction that the wave is traveling. Or you could say they vibrate parallel to the direction of wave propagation. Imagine you have a slinky spring. If you push one end of the slinky forward and then pull it back quickly, you'll see a pulse travel down the spring. That's a longitudinal wave. Notice how the coils of the slinky move. Each coil pushes the next one and then pulls back. The coils themselves are moving back and forth horizontally along the length of the slinky. And the wave, that pulse of compression, also travels horizontally along the slinky. The particle motion is parallel to the wave motion. This is the defining feature of a longitudinal wave. Section 7. Bouncing around. The science of reflection. Now that we know about different wave types and their properties, let's see what happens when waves meet stuff. First up, reflection. Reflection is what happens when a wave hits a surface and bounces off. It's like throwing a ball against a wall, it bounces back, right? Waves do the same thing. When a wave encounters a boundary between two different media, like light hitting a mirror or sound hitting a hard wall, some or all of the wave can bounce back into the original medium. This bouncing back is called reflection. It's a very common wave behavior. Think about looking in a mirror. You see your reflection because light waves from you travel to the mirror, and then they bounce off the smooth, shiny surface of the mirror and travel to your eyes. The mirror reflects the light. Smooth, shiny surfaces are great at reflecting light. That's why mirrors work so well. But it's not just light. Sound waves reflect too. If you shout in a big empty room or a canyon, you might hear an echo. An echo is just reflected sound. Section 8. Bending the rules. Unpacking refraction. Next on our journey of wave interactions is refraction. This is a really cool phenomenon. Refraction happens when a wave bends as it passes from one medium into another. Why does it bend? Well, it usually happens because the speed of the wave changes as it enters the new medium. Imagine you are pushing a lawnmower. If you push it from a smooth pavement onto thick grass, one wheel will hit the grass first and slow down, while the other wheel is still on the pavement moving faster. This will cause the lawnmower to turn or bend its path. Waves do something very similar. A classic example of refraction is a straw in a glass of water. Have you ever noticed how the straw looks bent or broken at the surface of the water? That's refraction. Light waves travel at a certain speed in air. When they enter the water, they slow down. This change in speed causes the light waves to bend, making the part of the straw underwater appear to be in a different position than it actually is. Section 9. Spreading the news, diffraction, and our wave wrap-up. Our final wave interaction to explore today is diffraction. Diffraction is what happens when waves spread out as they pass through an opening or around an obstacle. Imagine water waves in a harbor. If there's a small gap in the harbor wall, you'll see the waves that pass through that gap spread out in a circular pattern on the other side. They don't just travel in a straight line through the opening, they bend around the edges. This spreading out is diffraction. It's like the wave is trying to peek around corners. It's a very subtle but important behavior. You experience diffraction all the time with sound waves. Have you ever noticed that you can hear someone talking, even if they are around a corner or in another room with the door slightly open? That's because sound waves can diffract or bend around the edges of the doorway or the corner. If sound waves only traveled in straight lines, you wouldn't be able to hear them unless you were in direct line of sight. Light waves also diffract, but because their wavelengths are so incredibly small, the effect is usually harder to notice in everyday situations unless the opening or obstacle is very tiny, comparable to the wavelength of light.